So I'll tell you a little bit about this. I mean, this is really a potpourri insert, and that's why I call it hors d'oeuvres rather than the full meal, the full menu.
Wouldn't it be hors d'oeuvres?
Hors d'oeuvres, yes. And you know, my French is better than Steve's, but I still cringe at potpourri, Steve. But I know you're doing that on purpose to make me cringe. And so, anyhow, I got into this because Steve sent me a really interesting video clip or a link to it by Derek Muller, who works for Verasium and is a kind of Mark Rober figure, only for mathematics. And he was talking about p-adic numbers. And Steve said, should we talk about p-adic numbers to the LCTG? And I said, what are p-adic numbers?
Wow.
That's of course, my favorite thing to talk about is anything I don't know anything about, because then I have to learn something. But so I went and I watched a video that he sent me, and I watched it 3 times. And after the 3rd time, I began to think, well, maybe I kind of understand now what a p-adic number is. And then I made a list of about 12 subtopics that I thought we would have to go through and get everybody at LCTG to understand before we could go and talk about p-adic numbers. And along about then, Steve and I said, no, we don't want to bring this to the LCTG. But one of the topics that I saw as a subtopic was modular arithmetic. And so that also satisfied my ignorance principle that I can't remember who it was, but some physicist was once asked if he knew about neutrinos, and he said, no, I haven't even lectured about them. and, you know, and that's where I come in. And so, but modular arithmetic, I knew a little bit about, but I thought that for a potpourri, hear that, Steve? Potpourri. Anyway, I thought for a potpourri, I would like to talk about sort of 2 applications of modular numbers, or 2 places where modular numbers explain something interesting. So let me first show you what the interesting thing is, or what I think is interesting. And then maybe at the end, or when I get there, I can talk about how the let's see, I think I better just move this guy off a little bit.
You can.
I can get him out of the way a little bit. So I gave each a piece of paper and a pencil because I want you to do the following experiment. I want you to take a 4-digit number. I use the digits off my license plate, 9616, but you guys should make up your own 4-digit number. And then if you add up those digits, like the 9616, I add them up, and I got 15 plus 7. Then I add up the 7 and the 15, and I got 22. And then I added the 2 2s together. And so I sort of kept doing the addition until I end up with a single digit. And you can do that with a number of any size. And that number that you get at the end, the 4, is the remainder that you would have got if you had divided 9616 by 9. This will work for any number. And I always thought that was kind of cool. And indeed, people who have done financial work, at least maybe 100 years ago, or somewhere, or in elementary school, your math teacher might have talked to you about casting out 9s. And in effect, that's what we're doing. But so what did you get? Did it work for you? What did you use for a number?
I used 1463.
All right.
The year I was born.
Okay. So right away, I know that digit is going to end up at 5.
Mm-hmm.
And the way I did that was I immediately took 6 and 3, that's a 9, throw it away, and then add the 4 and the 1.
Oh, so mine ended up with a 9, but I guess you can't have a 9.
Well,
So
a nine
a
is no
zero.
remainder. Nine, it just means you should have divided by one more. So that, I would call that a zero. Means that your, whatever number you chose is exactly divisible by 9.
Gotcha. But this long process of getting to 4 here, you could also just add 9 plus 6 plus 1 plus 6.
That's what I'm doing, and I'm just showing you how. I
Okay,
do it.
okay. You were illustrating mathematics to us.
You can also divide that by 3 and you get the same result.
Yes, but 9 always works and 3 does not.
When does it not?
Well, for any,
I couldn't hear that question, Charlie. What do you mean 9 always works and 3 doesn't? I didn't understand the question, please.
so the business of adding up all the digits and getting the remainder always works for 9. It will not always work for 3. I mean, just let me see.
Well, the
It
rule-
turns out, Jerry, okay, you've hit upon another interesting feature. I'll come to that in just a second. Let me see. Does this work? No.
Well, Charlie, the rule for threes is that if the sum of the digits is divisible by 3, then the original number is divisible by 3.
Yes, you got it.
The
Now,
remainder is,
but here's another interesting feature. I'll get to that. That's my third interesting feature of nines. The order of the digits doesn't change the sum. If you apply this to any, you put down 4 digits and you added them up. Now, if you shift them around, you'll get the same sum. So that means all of these numbers, let's see, oh, come on. Yes, there we go. So here, the 12 distinct permutations of 9616 are all going to have remainder 4 when divided by 9.
well, because you're all single digits.
Those seems obvious, yeah.
Well, good.
You pretended it's a 4-digit number, but it's really 4 separate digits.
Well, it is in a way. I mean, every number is separate digits if you're going to make that statement.
Well, no, in other words, they're not tens and hundreds and thousands.
Well, they are, of course. We just treated them as single
As
digits, and it worked out. Now we have to understand why. What happened to all the ends?
Now, Charlie, this is a base 10.
This is absolutely base 10. At the end, I'll just mention what you can do some other base, but this is base 10. And here's the point that Jerry was making, I think you were making, that if the sum of the digits is 3, 6, or 9, the number is divisible by 3, and I chose 1776. It's a very Lexingtonian number, and you did the addition of the digits once again, and you end up with 3. So that tells me that 1776 is divisible by 3. I can also see immediately that 1776 is an even number, so it's divisible also by 2. So therefore, I know it's divisible by 6. And you get all this just from adding up these digits. And as I say, any length of digits, it works, any number.
Charlie, I don't want to dwell on the number you chose, 1776, but it is not a Lexington number. 1775 is the Lexington number.
Yeah.
Right.
Good
I don't
point.
want to pass any rumors.
All right.
This is being recorded.
This is being recorded.
Well, thank you, Harry. I'm sticking with 1776.
That's a great example, though.
It's, just because of the spirit of the
Oh,
thing.
it's spirit.
All right. And
And I noticed, Charlie, that you're changing your font.
yeah, well, I have 2 different fonts for reasons that I'm not going to
This is
explain.
not a talk about fonts.
But this division by 3 is kind of useful because you can immediately see the number 201 is not a prime number, and neither is 501.
Ooh, simple.
And yet I think I'll show you after a while that 101 is. 301 is not, as it turns out. But anyway, we'll come back to that because there's a kind of interesting application of modular arithmetic. So that's one interesting thing, what the nines will do in base 10, how you can check divisibility.
So is that what you just said? A speed up of when you're searching for 2 prime numbers like you are in RSA to do encryption, in other words, just run up through your numbers and you don't have to do other factoring, which is harder, it would seem.
Well, I mean, there's sort of it's in a category with all even numbers are immediately rejected. So you get rid of half the numbers, they're not primes, okay?
Right.
And then if you sum the digits, you can get rid of all those. And you can get rid of them because if there are 3, 6, 9, you can sort of get rid of a third of what remains.
If you read Richard Feynman's book, you find out that he was really amazingly good at doing all sorts of mathematical tricks because he knew a lot of these things,
Yeah,
some of
right.
which are
That's right.
going to hit today.
There are all kinds of kind of number tricks that people do. And very many of them are based on this property. So I've just told you about these interesting features, and in a little while, I'm going to try and come back and talk about why this is so, what this has to do with modular arithmetic. But we'll see. But before I do that, I wanted to show you what I thought. And these are hors d'oeuvres, and I have two. This is the first. I wanted to show you what the next is. Maybe my slides are out of order, but so this is going on to explain this first hors d'oeuvre. Gauss, so this business of working with remainders of the numbers has been understood for a long time. One of the earliest applications of modular, what we today might think of as modular arithmetic or a modular arithmetic problem, was by a Chinese mathematician somewhere in, I think, like the 9th or the 10th century. And as a result, we now have a theorem which is called the Chinese remainder theorem, which Gauss proved, Gauss being the mathematician that he was, gathered together a lot of ideas about the properties of these numbers and other features of numbers, and created an organized mathematical framework for discussing these things, which he called modular arithmetic. And the basic idea, let me see how badly out of order I am. The basic idea is that if you have a number, let's say A, and that number is always going to be equal to some integer multiples of a number which we call the modulus. So we've been talking about nines. We've been thinking of every decimal number as some multiple of 9 plus some remainder. So the number we were looking at was at 62 nines plus 4, I think. And so you can think of every number is made up of a modulus, and that's why I called it M, because he did 2, and so other people did 2. So you call that number the modulus, and then you can talk about the remainders, and he introduced this notation. This is Gauss's notation, that you take a number, let's say, say it's 12, and the modulus is 5. Then you're going to divide the 12 by 5, and you're going to have a remainder of 2. And so you'll be writing down 12. Whoops. You'd be writing down 12 is equal to 2 mod 5. 12 is equal to 0 mod 4. 12 is equal to 0 mod 6. 12 is equal to 5 mod 7. So you see, as you change the modulus, you're going to get different remainders, but this notation will take care of that.
And the old favorite, 12 modulo 10
Will be
2. So that's the one we're used to.
Right. And if you okay, but if you do 12 modulo 9, you already know the answer because you worked it out before. It's the sum of those 2 digits. That's what's kind of neat about modulo 9 and base 10. If you were in base 6, then the number that's 1 less than the base number is 5. You go 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, 15, 20, 1, 2, 3, and so on. Well, this will work with, in base 6, it will work with the 5s. The sum of those digits will be the remainder of whatever number base 5. All right, now what Gauss, well, what was kind of vaguely around, but what Gauss pulled together was that the modular numbers form an arithmetic, because if you have two numbers base m, then it will turn out that their remainders, and you add them, their remainders will add. That's a little tricky because you might say, okay, 10 mod 7 is 3, and 12 mod 7 is 5. So if I add 12 and if I add 12 and 10, I'm going to get 22, and 22 mod 7 is 1. Yeah, but before I had 5 and 3, so I'm saying that the mod is 5 plus 3 is 8, but I have to divide it by, I have to convert it by the modulus. And 8 mod 7 is 1. And so in that sense, the remainders will continue to add. When you add the numbers, their remainders will add mod 7 in that particular case. And they will subtract in the same way. I was giving you 10 mod 7. Everybody okay with that? 3. And 12 mod 7. 5. And I add 12 and 10, and I get 22. And 22 mod 7 is 1. 7 goes into 22 3 times, 21, 1 left over. All right. And now we did the sum of the two numbers came out to be 22, and the sum of their remainders came out to be 8. But we don't have an 8 mod 7. We have a 1. 8 mod 7 is 1. So that is the way the addition of modular arithmetic is to work. This works for the difference. So if I took 12 minus 7, I'm sorry. If I took 12 minus 10, I would have 2. And if I took the difference between their remainders, 5 minus 3, I have 2. So the remainders follow this arithmetic. If I took 12 times 7, I'm sorry, if I took 12 times 10, that's 120. And the product of the two remainders is 15. But 15 is mod 7 is 1. So 7 goes into 121, 7 goes into 57 times, 49, and I got 1 left over. So that's it. I'm not going to explain a division because division is really tricky, but there is a division. And so there is an arithmetic of these remainders following the rules that we see coming out for us. And now this was my second hors d'oeuvre. You know Fermat's last theorem. That's, or at least even if you don't know what it is, if you can't remember what it is, you know it's famous. But there's another thing which is also known as Fermat's theorem, which is not the last theorem. So maybe it's the one before the last, I don't know. But it's also called Fermat's little theorem, and I'm just calling it Fermat's prime number theorem because I think that'll do us better. But I like to think of it as Fermat's theorem. And of course, Fermat, like Gauss, famous mathematician, although what he really was a lawyer who liked to do mathematics in his spare time. Even though he turned out, I don't know, he may have been as good a lawyer as he was a mathematician.
Fermat's last theorem about the number comes the map.
No, what? Fermat's last theorem, of course, is that you can have Pythagorean relationship is x squared plus y squared equals z squared, and you can find integer solutions, 3, 4, 5 being the most famous one. but you can't do it for any other power than 2. And Fermat wrote in the margin of his notes of the book he was reading at the time, I have a wonderful proof that you cannot do this for any number bigger than 2, but it's too big to fit in the margin.
And then it proceeded to die, right?
And then he died. And 360 years later, or whatever it was, Andrew Wiles came up with a solution using mathematics that none of us understand.
But didn't it also take like 1,000 pages?
Yeah, and you know, and it was not right. I mean,
First time.
well, it took a lot of people then sort of chewed on it, but he's the
I
hero.
know it.
He's the hero. All right. now let
That's
me
the
see.
mathematical version of Schubert's unfinished symphony.
Is it? I mean, Schubert. The thing I like about Schubert's unfinished symphony is that he actually started it when he was quite young. He did not die and leave it. I mean, he did die and leave it unfinished, but he just left it unfinished for much of his life. And
I have a lot of those.
That's why Schubert's last symphony was the 9th. The unfinished is the 8th.
okay, so let me see here. Something has gone wrong with this. All right. So
There's an AI system, by the way, that was used to finish Schubert's 8th. And it actually sounds pretty nice.
All right. So I've lost track of a slide, but Fermat's last theorem says the following: if you have a prime number, you can take anything that has not got that prime number as a factor. Take any other number. So let's take 5, a prime number, and let's take 2. You can take 2 to the power of that prime number less 1. So take 2 to the 4th. And divide it by the prime, and you will have a remainder of 1. In other words, 2 to the 4th power modulo 5 will be 1.
Well,
See? This is true for any prime number, no matter how small, how large, and for any number that you choose to take that power. So we could also do this, because it's within our capacity, do it for 3 and prime 5. So you're going to take 3 to the 4th power. That's 81. Divide 81 by 5, you got a remainder of 1. Yeah. Another way to say this is that take 2 to the prime number minus 1, take it to that power, and then subtract 1 from the result, and it will be exactly divisible by the prime. In other words, we take 2 to the 4th power, get 16, and subtract 1, we get 15, exactly divisible by 5. They're just equivalent ways of saying the same thing. So that's Fermat. I mean, Fermat proved that so we were looking at 201, and we saw immediately that's not a prime. So if you were to take 2 to the 200th power and divide it by 201, the remainder would not be 1. It would be something else.
that's not a problem.
Yeah. So, but we know it's not a prime without having to do anything fancy, which is nice. On the other hand, we're not sure about 101. So we might like to take 2 to the 100th power, and we could subtract 1 from that, and it should be divisible by 101. That's the 2 to. So the general formula is 2 to the p minus 1 divided by p, or 2 to the p minus 1 is equal to 1 mod p, is what the formula is. So it's just very nice. It's just kind of pretty, and it isn't all that you'd like, but you said, well, 2 to the 100th. Who's going to calculate 2 to the 100th? That's 30 digits long, and it's a big number. Now, this is actually a quirk of a personal quirk, that you probably, I mean, I told you about it 3-4 years ago when I first joined, but I like to do this kind of stuff in my head. Usually about 4 a.m. Okay. And it is a way to go back to sleep. And sometimes it'll take me 3 or 4 nights because I will fall asleep trying to do the calculation in my head. But how do you do 2 to the 100 in your head? And I can. And I can because of modular arithmetic, because, and I'm using now that multiplicative feature of modular arithmetic, that the product of two, the product of the remainders of 2 factors, said it wrong. You have 2 numbers, mod something, they each have a remainder. If you multiply those 2 numbers together, the remainder, their remainder will be equal to the product of the original remainders. So let me just see if that's true. It's something we could do. 2 to the, so we take 17 mod 5, that's 2. Take 3 mod 5, that's 3. Take 3 times 17, that's 51. And you notice that what do we have? We had 2. So we had, oh, I forgot my numbers. To write that down there?
You minus 73.
I said,
Multiplying 7 times 13,
Uh,
3 times 17.
this 51.
51.
Yeah, but I was,
Mods are 3, and the 17 is, what is it, mod 7? Mod
it's 3 also.
3 also.
Yeah. So the product of the 2 mods, the two remainders is 9, which is 2 mod 7.
Right.
And the and well,
Why do I care?
I've blown it somewhere in there.
We'll have to wait for
I have
4
to, I
a.m.
really do this best when I'm lying down on
See you
my
at
back.
4 a.m.
Now,
Huh?
It's at 4 a.m.
Yeah.
I remember in high school when I was trying to do things like that, it would start off by saying like 2 to the 6th is 64.
Yeah, well,
So 2 to the 12th would just be 64 to the 64. I don't have to multiply by the 2's all along.
well, so here's my calculation. And I'm putting down 2 to the 10. I decided I would start with, because I know 2 to the 10.
1024.
Yeah,
Right.
I mean, we all know 2 to the 10.
Right.
Anyway. And I like 2 to, I also like that I'm looking after 101 because 101 divides nicely into a whole, it's easy to divide with. I mean, 1024, and I say, oh, well, 10 times 101 is 1010. And so the difference is 14. So that remainder, so 1024 equals 14 mod 101. That's 2 to the 10. 2 to the 20 will have a remainder, which is 14 times 14. Because 2 to the 20 is 2 to the 10 times 2 to the 10. And the remainders of each of those are 14. 14 squared is 196. And now I'm doing some cuteness because you can have negative values. In other words, I didn't say, as I talked about modular numbers, but you probably had run across them as clock numbers at some point. You know, and indeed, that's right. If we're talking about 7 modulo 5, we think we're going around the clock. We're going to go 5 units around my clock, which is 5 units, and then I'll go 2 more, and I'll be at 2 on my clock. And if I go 12 mods 7, I'll go around 7, and then I'll go 5 more, and I'll be at 5 on the clock. But I could have gone backwards.
Because the clock was developed by somebody with 12 toes.
You're one of those kind of cats. Yeah. Anyway, you go backwards to 12. How far, you know, so you're going to start at 0. And say, what are we doing? We're doing mod 7. We're doing,
Backwards into minus.
actually, we've gone around 12. And so we're too short of being at 0. And so we're at -2. And -2 works just fine in modular arithmetic. And I wanted to do that because it just makes this calculation, I can do it in my head much more easily. So I got 14 squared is 196. I could subtract 101 from that, and I would have a remainder of 95. But it's much easier for me to say, no, let's go up to 202. And then I'm 6 backwards from that. I'm at -6. And then I'm going to do, so I'm saying, oh, okay, 2 to the 20th is -6, mod 101. Well, I want 2 to the 40th. I'm going up. Well, 2 to the 40th is -6 squared, and that's just 36.
But that's also how I taught my kids long division, so that if they could move the numbers around a little bit, they get an approximate number. And then when they did it for real, they'd see whether their answer was more or less right.
I mean, that seems to me like good technique. I'm not sure you're doing modular arithmetic quite.
No, it isn't, but it's,
Anyway, so I'm now at 2 to the 20 times 2 to the 20. That's 2 to the 40th. And I know that its remainder divided by 101 is going to be 36. That's that -6 times -6. And now I can say, okay, well, 2 to the 80th is going to be 36 squared. And I can square 36 in my head, especially when I'm half asleep. And I'm going to get 1296. And then I'm going to divide that by 101. And now I actually have to do it. I'm going to have to take 101. That's going to give me 286. And then I'm going to take 286. And I'm going to use 303 because 286 is 17 away, is -17. And then I say, oh, I got 2 to the 80. Oh, well, way back there, I had 2 to the 20. And 2 to the 20 was -6. So I'm going to take 2 to the 80 times 2 to the 20. And the remainders are -6 times -17. That's 102. And what's 102 mod 101?
1.
I love it. It just sort of gives me a thrill that I mean, Fairmont told me it was going to happen, and I really believed him, but I still like to see it work out. And that's kind of the thing. And that's where I come to a stop with my second hors d'oeuvre of
So do you think Fermat came up with this theorem just by, I have a bunch of examples and they come out the same? I think I'll call this a theorem. It must be a theorem.
No.
That's how us engineers come up with theorems.
No.
No.
I mean, I mean, I think there's a kind of progression from engineers to physicists to mathematicians.
Right.
So I'm kind of halfway in between, you know. I don't mind doing mathematics the way engineers do. And I cannot do mathematics the way mathematicians do. I mean, it's just, it drives me nuts. And this is sort of kind of engineering mathematics. I'm just playing with it, and because I enjoy playing with it. But there's more to there's a lot more to be said, and I leave you with the Chinese remainder theorem because the Chinese manuscript says, let's see, you have some quantity of things that if you divide by 3 has a remainder of 2. And you have the same quantity of things. If you divide them by 5, they have a remainder of 3. Or if you divide this quantity of things by 7, you have a remainder of 2. What's the smallest number of things? And that's a classic problem and so this is in an old Chinese manuscript from far, far away. So you can use this kind of mathematics. You can actually show that there is a solution. There's only one solution, and that is the Chinese remainder theorem. It's called that because it's understood to have sort of derived out of that historical
Well, what kind of numbering system did the Chinese use? And we use the Arabic numeral system. What did they
I
use?
don't know that, Jerry. That's an interesting question.
Ask ChatGPT.
I've been very disappointed with ChatGPT.
I gave ChatGPT this problem. Actually, I had not understood the statement of the problem, and I thought rather than using moduli 3, 5, and 7, I thought they were using 9, 25, and 49. And I asked ChatGPT what the answer was. And ChatGPT gave me an answer. Was absolutely wrong. And then I looked at it and I said, ChatGPT, isn't this number supposed to be divisible by 3 with a remainder of divisible by 9 with a remainder of 2? And ChatGPT said, "Oh, I'm very sorry. I made a mistake here," and gave me another answer, which was absolutely wrong. Okay, I got one more thing to say about this, and then I'm done. And it is the sad thing, because we've shown here that according to the Fermat's theorem, 101 satisfies that relationship. Does that mean 101 is prime? And the answer is no, because that is I can't remember the converse, inverse, and so forth of a logical structure. This does not mean that the thing is prime. If it were not 1, it would definitively tell you that the number is not a prime. That's absolutely correct. There are composite numbers that satisfy this relationship. So when you find this relationship is satisfied, you do not know that it's prime, and therefore NSA has a huge job, because if they didn't, this would help. I am done, Steve. The fact that the Fermat's theorem does not assure you that what you've got is a prime number is my closing remark.